We turn now to the issue of entropy and the development of the second law of thermodynamics. And we saw in the previous chapter that we built the Carnot cycle on the shoulders of the first law of thermodynamics. And the first law of thermodynamics concentrates on energy. So we looked at the internal energy of the system, delta U. We looked at the enthalpy, delta H, of the system. We also investigated the relationship between heat and work. And in particular, we wrote the first law of thermodynamics as delta U, the change in the internal energy of the system, as the sum of the heat plus the work done on that system by the surroundings. We also defined enthalpy. Enthalpy is equal to the change in internal energy plus the change in the product of pressure times volume of the system. And that led us to deduce the fact that the change in enthalpy was equal to the heat released at constant pressure. And since 95% of all chemical reactions occur at constant pressure, that delta H term turned out to be the most important variable for analyzing the energy of a system. But now we look at some different examples of processes in nature. We have corrosion, where iron is converted to iron oxide, and as we'll see in this case, delta H is less than 0, but only slightly less than 0. And of course, when delta H is less than 0, the reaction is exothermic. It releases energy. It's spontaneous because it releases energy to the surroundings. Now, if we conflagrate gasoline, now we have a release of chemical energy, a change in enthalpy that is not only less than 0, so it's releasing energy to the surroundings, but it releases a massive amount of energy. But that's not the whole story, because if we look at ice, which we are intimately familiar with, and we hold that ice at 0 degrees Celsius, which is the freezing and melting point of ice, it turns out if we hold it at that temperature, ice melts. And yet it takes energy going into the system in order to melt that ice. So there's some other force of nature that's coming to bear on whether a process, a reaction, or a physical process is spontaneous or non-spontaneous. If we look at lava flowing into the ocean, we know intuitively that the heat that's intrinsic to that lava, when it goes into the ocean, is going to disperse through the ocean. But why is that? Why is the dispersion of that energy into the water spontaneous? What force of nature, what aspect of nature creates that? And then we can get more sophisticated. We can look at methane clathrates, where methane is captured inside a network of ice. And this process requires no additional energy, yet it's so ubiquitous, it's so common in nature, that the chemical content of these methane clathrates has an energy content 3 times the total of all coal, natural gas, and petroleum reserves. A massive amount of chemical energy, which is stored there because nature abhors a vacuum. It wants to insert those methane molecules into that cage of water. But why is that? How can we describe that quantitatively? And so if I were to ask you the probability that the heat that's in the ocean flows back into the lava, you'd burst out laughing. It's impossible. Impossible. That means there's a probability associated with the definition of entropy. There's also an issue of organization versus disorganization. If that heat is coming in through the hot lava and it's distributing itself through the ocean, that system is becoming more and more disorganized because the heat that's flowing into the microscopic motion of those molecules is inexorably moving outward constantly to a more highly disorganized state. And to see that, you can run backwards from the heat distributed in the ocean back into the lava, and you see the concentration of that energy in the lava is far more organized than it is as it diffuses out into the ocean.